is a question that you could do without doing anything in chapter 17. This is stuff I should be able to hand to you, and you should be able to do it. Or at least you have a vague recollection of what it was talking about, and you could probably figure it out eventually. Alright, so for example, you're one space short of winning a child's board game and must roll a 1 on a die to claim victory. So you can't get a 6 and move to one space. You have to get a 1. You know some games are like that. You want to know how many rolls it might take. So in part A, it says describe how you would simulate rolling the die until you get a 1. So in part A, it wants you to describe a simulation like we did in chapter 11. So there are some pieces to a simulation. For example, what would the component be? Rolling 1 die, right? Okay. What would you do to simulate a trial? What would you do? Roll a die until you got a 1. That might mean you roll a die once. That might mean you roll a die 35 times, right? You would just go until you get a 1. I skipped the assigning numbers part because I'm pretty sure we're all on the same page that when you're rolling a die, the numbers are 1 through 6. Okay. And so then you would run 30 trials, and at the end you would look at the average number of rolls it took to get a 1. Right? Yes? You guys could do that. You could run 30 trials. If you want to see my homework, I have 30 trials. Okay, so you could do it. You could have done it in chapter 11. I could have given you that question. It wasn't even a very hard question. You guys could do that. Right? Remember when you thought chapter 11 was hard, and now you're like, oh. All right, so then on part C, it says, based on your simulation, estimate the probabilities that you might win on the first roll, the second, the third, etc. So it's saying, look at your simulation and decide. So on my simulation, the probability of getting a 1 on the first roll. Well, I had 30 trials, and I got a 1 2 times. That's what it was asking you to do. You could have done that. You could have done second, third, fourth. Problem is there's no end point, right? Like one of my trials, it took 28 rolls of a die to get a 1. I know that's a lot. So I would have to keep going with these probabilities all the way up to 28 for them to add up to 1. That's annoying, right? On D, it says calculate the actual probability model. We've been talking about probability models. So if X is your number of rolls to get a 1, then there's, again, a variety of possibilities. You could get a 1 on your first try. What's the probability of getting a 1? 1/6. Exactly. All right, on number 2. You could get a roll on the 1 on the second roll. That means you didn't get a 1 on the first one, and you got 1 on the second one, right? And I would keep going. But there are infinite possibilities, right? Like, I could just keep doing this forever and ever. And then it says compare the distribution of outcomes in your simulation of the probability model. So like on mine, the simulated probabilities are much different than the probability model. The probability model is like actual probabilities. The simulation is just what happened in my graphic calculator, right? So that should be different most of the time, right? But in chapter 17, we're going to talk about there has to be an easier way to do this. There has got to be an easier way to answer the question, what's the probability that I get a 1, than doing this infinite probability model, this infinite simulation. Okay? Does that make sense? So in chapter 17, we're talking about probability models. And there are 2 big models we're going to talk about. One is called the geometric model, which we're going to talk about today, which you've actually kind of already used before. And one's called the binomial model, which we'll talk about later this week. There's some other stuff in chapter 17, but these are the 2 major things I'm going to focus on. Now, these are probability models that are very specific. And I don't know why, because last year they couldn't keep them straight, but they don't do the same thing. they don't do the same thing. So I don't know why it was such a struggle. So this year I'll try to make it not a struggle. Okay? So before we do anything with probability models, I'm going to talk to you a little bit about a Bernoulli trial. Okay? Our book is talking about, in this beginning of that chapter, it's talking about that simulation with Tiger Woods, Serena Williams, and David Beckham cards in the cereal boxes again. Remember that? They're talking about it again. And so they just went through and said that they don't want a complete set. Because most of the ones we did in Chapter 11, you had to have a complete set of those cards. They're like, I don't care if I get a complete set or not. I just want a Tiger Woods card. That's all I'm worried about. I just want a Tiger Woods card. So they were starting to look at the probabilities of getting a Tiger Woods card. So what's the chance of getting a Tiger Woods card, right? So what's the probability that it was in the first box? 20%. What's the probability that you got your first Tiger card in the second box? 0.8 times 0.2, right? Stuff that we have done before. What's probably that the first Tiger card was in the third box? Well, that's 0.8 to the second times 0.2, right? Okay? So, what's happening is they're using this concept called a Bernoulli trial. So let me define what that is for you. Because you have to use Bernoulli trials in order to use a geometric model or a binomial model. And in Bernoulli trial, you have some things going on. First thing, you can only have two outcomes. That's all you can have. So in the Tiger Woods cereal box situation, they were only worried about Tiger Woods cards, so there was only two outcomes, Tiger Woods or not. They list some Bernoulli events like tossing a coin. You can only get heads or tails. You might have an event that has several outcomes, but you're only concerned with one, so it's that part of the event or nothing. That would be two outcomes. So if you can narrow your focus and the probability to two outcomes, maybe you can use a Bernoulli trial. You also have to have independence. So your events have to be independent. So your cereal boxes, we were assuming the cereal boxes were independent. That the first one didn't affect the second one. Right? Opening the first box and getting a Tiger card does not mean that this next one's not going to have a Tiger card. Right? If you're flipping a coin, flip a coin, you get heads, you flip it again, you could get heads again or tails, it doesn't matter. Right? So you have to have independence. We're going to come back to this idea in a little bit because I'm going to add one extra step to it. But in general, Bernoulli trial has two outcomes and the outcomes are independent. Now there is some notation / statistical language here. Your two outcomes have separate probabilities, right? You have a probability of success and we denote that with a P. So if you're talking about the Tiger Woods cereal boxes, the probability in the Tiger Woods cereal box is 0.2. That's my probability of success. My probability of failure is then Q, and it's the complement. So if getting a Tiger Woods card is 0.2, then not getting one is 0.8, like we did earlier when I wrote some numbers down at the top, right? So tossing a coin, looking for defective products, rolling off an assembly line, defective or not, shooting free throws, hit or miss, those are types of things that could be considered Bernoulli trials. So before we go any farther, we're going to look at just some situations and talk about Bernoulli trials, okay? We're only going to do A, B, and C and come back to D and E in a little bit after I talk about some other things. So all I'm worried about is, do these situations involve Bernoulli trials or not? So on A, we roll 50 dice to find the distribution of the number of spots on the faces. If you're looking at a die, looking at the spots on the faces, the die, each roll is independent, right? But do you have just two outcomes? No, how many outcomes do you have? 6. So this would not be a Bernoulli trial because you have 6 outcomes. Bernoulli trials only have 2. questions about A. On B, how likely is it that in a group of 120, the majority may have type A blood, given that type A is found in 43% of the population? Are people independent of blood type? Yes. Can we narrow this? Does the focus narrow enough that we have two outcomes? Yeah. Type A or not. They're not worried about, they don't mention any of the other blood types. They're just worried about being type A. If you're not type A, they don't care what you are, right? So you have type A or not, and these events are independent. So this is yes. You've met those two criteria so far. And then in C, we deal 7 cards from a deck and get all hearts. How likely is that? So, do you have two outcomes? Yeah, hearts or not, because they're talking about hearts. Are these cards going to be independent? No. You take a card out, and you get a heart, you reduce the probability for the next one, right? You're drawing without replacement. So this is no, because they're not independent. So again, I'm giving you lots of building blocks today. Bernoulli trials will come up more in the consecutive days, but it's important to start here, okay? Because everything we're doing is going to be a Bernoulli trial in this chapter. Questions so far? We good? Okay, we'll come back to those last two in a second. So at the beginning we were talking about that simulation with the rolling a 1 to win the game. The book is talking about the tiger card. They're trying to get a tiger card. There has to be some easier ways to find some probabilities when you're looking for specific things. So we have the geometric model. And let me tell you very clearly what the geometric model does. The geometric model gives you probability, all right, for the number of trials until your first success. So for that dice game, I want to know the probability that I roll a 1 on the 4th attempt. Or I'm doing something with flipping a coin, and I want to know the probability that I get ahead on the 7th attempt for the first time. So geometric model concerns itself with the first success. Okay? It's very specific. I really don't know how we could get geometric and binomial messed up later this week, because geometric is just talking about the first success. So if you equate geometric and first in your mind, that's going to be great. Okay? Now, back in chapter 6, we talked about the normal model, right? And it had some notation with it. So the normal model had notation where we would say n and then mu and sigma. That told us what model we were using, which bell curve we were thinking about, right? For the geometric model, we also have some notation. We use geom p, where again p is your probability of success. Okay, yeah. And then you have to have Bernoulli trials. If your events aren't Bernoulli trials, you can't use this model because it hinges on the fact that there is a probability of success and a probability of failure. So if there's more than that, then you can't do this. You have to have two outcomes. Now here's the issue. I'm going to do some examples today after a little bit. We're using this model, and you're going to say, yeah, Ms. Haltman, I could have done this without this. That's fine. But again, I'm going to give you some building blocks. Later this week, this will be important. Okay? Okay. Ever. No one ever. The probability part of this is going to be fine. No issues. The problem is going to come when I start asking for expected values or standard deviations, because there's not an actual table model. All right, so the next slide is going to help you with that. So here's the actual geometric model. And it says you have P is the probability of success. So then they use Q as the probability of failure. That's not a standard thing. You'll see a lot of textbooks just leave it as 1 minus P, because that's all it is. Right? There's two outcomes. So if one is 30%, then the other one has to be 70, right? They have to add it to 100. So our book will use Q. The AP formula sheet kind of stuff always uses 1 minus P. They don't use Q. Again, X is the number of trials until the first success. Now let's talk about what this means. Let's say, this is my question. What's the probability that my first tail on a coin is on my 7th flip? Okay? That's the kind of specific question the geometric model can help you with. You could have done that before. You did it on the Chapter 14 quiz. Okay? So how would I find that probability? You would do heads for the first 6, right? What's probably getting a head. 0.5 for the first 6 flips. And then getting a tails is also 0.5. But that's what that formula is saying. It's saying Q to the x minus 1 power, because it's saying you don't get what you're trying to go for the first so many times, and the last time you do get it. What if I did the probability that my first 5 on a die was rolled on my 10th roll? Again, you could have found that probability before. That means 9 rolls I didn't get a 5. What's the probability of not getting a 5 on a die? 5 out of 6. So that's 5 out of 6 to the 9th power, because 9 rolls I didn't get a 5, and then I got a 5. That's what this notation is talking about. Probably that you didn't get it for however many times, and then I got it. You could have found those probabilities without this model, correct? Probably. Again, bigger picture coming later this week. What I do need to know, though, is these equations for expected value and standard deviation. I don't have those anywhere else. So we did probability models in Chapter 16 with random variables. We had a table. We could find the mean by doing that weighted average type concept. We could find the standard deviation using the variance, right? Now we don't have that table. We don't have a table like that. So these equations are important. These equations are not on the AP formula sheet. The ones with the other model are this week, but these are not. I will tell you that very rarely are you asked about the standard deviation, but you are almost always asked about the mean. If you can't remember that's 1 over P, I mean, it's probably the hardest formula ever. 1 over the probability of success. If you're interested in where that comes from, most of you are not, but if you were, there's a math box in your textbook that goes through the proof of where that came from. I know, that's what I figured. All right, one more little bit, and then we'll do some examples. Now, we talked about independence a little bit. For like flipping coins and rolling die, and even like cards, that's easy to figure out if they're independent or not. But what if we're not talking about easy, like normal statistic probability stuff? Like what if you're talking about these cereal boxes? Okay? If I know there's 10 cereal boxes on the shelf, and I know ahead of time that there are 3 Tiger Woods cards in that 10 boxes, then are those events going to be independent of each other? If there's only 10 boxes and I know there's 3. No, if I get 1, there's only 2 left out of however many boxes, right? Those are not independent. That's like drawing without replacement with cards. But what if we're talking about like all of the cereal boxes in the land? All right, and I don't know how many Tiger Woods cards. It says about 20%. That's what the percentage was. That's 20% of this like an infinite amount of cereal boxes, right? I'm just picturing this big factory full of cereal boxes. Okay? If there's so many cereal boxes and I'm only checking 10 of them, does that change the probability a whole lot? Not really. Okay? So, here's your rule for independence when you're not sure. Your Bernoulli trials must be independent. If that assumption is violated, it is still okay to proceed as long as the sample is smaller than 10% of the population. So if you aren't sure if they're independent or they don't seem independent, it's okay as long as your sample is 10% or smaller than the population. Because then that means the probabilities aren't getting affected enough to even matter. You're making these minute changes. So earlier when you wrote Bernoulli trials, they had to be independent. If you weren't sure, it's okay as long as it's less than 10% of the population. So I want to go back to those Bernoulli trials we did earlier. Okay? And I'll come back to the screen in a second. Let's look at D and E. It says we wish to predict the outcome of a vote on the school budget and poll 500 of the 3,000 likely voters to see how many favor the proposed budget. What's your sample size? 500. And they tell you the population. Is 500 less than 10% of 3,000? No, definitely not. That's a very large sample. So if you start asking people in the population, you're reducing those probabilities, it's making a greater impact. So on D, these can't be Bernoulli trials because 500 is not less than 10% of 3,000. Okay? So we can't say those are independent events. If you're not sure, like on A, B, and C, we could tell they were independent regardless. But if they give you a number that they sampled, and you can estimate the population, then it's got to be less than 10% to say they are independent. And 500 is not less than 10% of 3,000. On E, a company realizes that about 10% of its packages are not being sealed properly. In a case of 24, is it likely that more than 3 are unsealed? Well, you have two outcomes, sealed or not, right? And then you're talking about 24 out of all of the packages in this factory or this company. Do 24 seem like it's probably less than 10% of all the packages that they're doing? Probably, right? If it's a successful company, you would hope they have way more, much more inventory than that, right? So we would say these are independent because they have, in the Bernoulli trials, they have two outcomes, and we can say that 24 is less than 10% of all packages. It would say something about it being a very small company or something otherwise. So this would be yes. Okay, so that gives you a when in doubt, there's the independence rule. Okay. You have to start remembering these conditions because after Christmas, that's all we're going to talk about is conditions, 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 assumptions, assumptions, assumptions. So for now, this is an easy one. Bernoulli trials, two outcomes, independence. They're independent, I say less than 10% of the population. Let's see some examples really quickly. And then tomorrow I'll come back and do all the notation about why this would have been different. So on 9, a basketball player has made 80% of his foul shots during the season. Assuming the shots are independent, find the probability that in tonight's game and there's 3 choices, or 3 problems. We don't actually have to use the geometric model all fancy like. You can just find the probability today, okay? So what's probably that he misses for the first time on his 5th attempt? Well, does that mean it happens on the first 4? He makes it the first 4 times, so that's 0.8 to the 4th power. And then he misses for the first time on his 5th, so that's 0.2. You guys again could have done that probability before. We'll bring this all back together why the model is important later. On B, makes his first basket on his fourth shot. So what happens on his first three? Right, he misses and then he finally makes it. Again, you guys could have done that before. C is a little bit tricky. It says makes his first basket on one of his first three shots. So in this case, you're going to stop when he makes his basket, okay? So if he makes the basket first, that's a probability of 0.8, right? But he could miss the first time and then make it on the second shot, or he could miss twice and then make it on the third shot, right? We're looking for the first basket on one of his first three shots. And then you would add all those together. Sounds a little bit tricky, but I think that's manageable. Questions about C? Yeah, you would. I got 0.9 something. Sounds about right. I got 0.992, but I could have done... Let me try that out and see if it works. Good, yeah, that's fine. Perfect. We're going to come back to this problem tomorrow and use the model, and I'll show you how to use your calculators, and that's why I'm doing it this way. On 11, you have to use the model a little bit. It says for the basketball player in exercise 9, what's the expected number of shots until he misses? What does expected number mean? Mean. What's the mean of the geometric model? How do you find the mean of the geometric model? What was the formula? 1 over P. P is the probability of success, but that's a weird term. It's the probability of what you want to happen. So we want to know until he misses. What's the probability that he misses? So it's just 1 over 0.2, which is 5 shots. So you'd have to use the model a bit there, right? You couldn't do that otherwise. For the geometric model, which we've been talking about today, we wrote down the mean as 1 over P. And P is the probability of whatever we're trying to achieve here. Okay, we'll talk more about this model again tomorrow. I've got how you can try to do it in the calculator, lots of different things, okay? So I've got a few homework problems, not things we've done today. It's not a big deal. 401, 1 second, 1, 8, 10, and 12.